Hello everyone, welcome to another video. In this video, we'll go over potential energy. Just a heads up, this is going to be a long video, but I'll break it down into timestamps. So the first, we'll recall work and energy. Now this might seem redundant, but starting at the base gives us something to build up on. So consider the following block. It rests on a smooth surface, no friction. You apply 10 Newton force and you move it 20 meters. You move it a distance of 20 meters. Okay. And then you just leave it. After it reaches this point, you just stop pushing it. And it just moves away with whatever energy it gained. So how much work did you do? Work equals force into distance traveled in the direction of force. So you use 10 Newton force and you traveled 20 meters in the direction of force. So you gave it 200 joules of energy. Okay. You did 200 joules of energy. You did 200 joules of work on this object. That means the object's energy increased. It became kinetic energy, as this object right now moves with that much energy to the right for eternity. But your energy, if you pushed it, your energy decreased by 200 joules. That's the amount of energy that you transferred to that object. Okay, let's think about something else for now. So we have guy number 1, a green skinny guy with a big head, and we have guy number 2, a rich green skinny guy with a big head. Now guy number 2 gave number 1 $1,000. So guy number 1 gained $1,000. So in a weird way of thinking, guy 1 did give the rich guy something. That's negative $1,000. Now it seems weird until you do the math. So the rich guy gained negative $1,000. So if you just add it, he lost $1,000. Now this seems to be very weird and a bit unnecessary, but keeping this idea at the back of your head will allow you to see problems differently. Okay, now we can move on to the definition of potential energy. Now loosely speaking, potential energy of an object is the energy stored due to its position in the field. We'll work with it a bit. So why did we even have to have potential energy? Like, what's the need of having potential energy in the first place? That's not something we really think about a lot. So let's say you pushed an object 5 meters up and you kept it there. You lost energy and that object gained energy. Now, before you rush to saying potential energy, let's have fun with it a bit. That object did not gain chemical energy. There was no chemical change. It did not gain heat energy. It did not get any electrical energy. Kinetic, you kept it there and you just stopped. So no kinetic energy, nor any internal energy. You'll know later. And there is no super magical hidden energy as well. So let's try another scenario. You moved it 10 meters up and you did more work. And in the same case above, you did not do any chemical, there was no change in chemical energy, no heat, no electrical, no kinetic, no super magical energy. So there must be another form of energy that depends on position. Specifically, where it is in a field. So for pushing it 10 meters up, you need to do more work. So there is energy at this point stored just because you moved it 10 meters up. And there is a smaller amount of energy that is stored in this object just because you moved it 5 meters up. And the energy required to move it 10 meters up was in fact higher compared to moving it 5 meters up. So in this case, what you did was you did work to move it against a gravitational force. Okay. Now moving on to gravitational potential energy, which is, you can say, the crux of today's topic. Now before dealing with gravitational potential energy, we could deal with gravitational potential. Now here you have the Earth and its field, which is extremely exaggerated. Now assume an object is moved from the infinity to a green point. Any of these green points. In fact, anywhere in these green points, you will have the exact same potential. Just because all of them are at the same distance. I was terrible at drawing the circle, so it doesn't look like it. Anyway, gravitational potential energy is the work done to bring this object from infinity to this point. And gravitational potential, phi, is the work done per unit mass. So this is the definition of gravitational potential, work done to bring a unit mass from infinity to the point. Now, how can we relate this to something that we already know? So from your O levels, or basically early high school, GPE was given as mgh. What potential states is gravitational potential energy per unit mass. So you divide mgh by m and you get gh, which is the potential. But this formula itself is highly limited. But let's actually apply it to something much more fruitful. So potential, we are going to use this basic term gh. So gravitational field strength, or G. Okay, let's actually look at this. G here is the gravitational field strength. So G is the gravitational field strength, and you multiply it by the height. So from Newton's law, G is minus Gm. M is the mass of the larger object, divided by r squared. So phi is just gh. So this is g. This right here is g. So if we multiply it by r, we get phi. Now this is a helpful idea, but it's not mathematically accurate. But let's go on with graphs, because that will give us the right mathematical idea. So let's start with this graph. This graph right here is the graph of force versus distance. And this is the graph for the diagram above. So you apply a constant force throughout this entire distance. So the area under the graph is F into D, which is equal to the work done. So we can say that the area under force distance graph is the work done. But we can also say is the area under field strength versus distance graph is going to give you the potential. Now here I have the field strength versus distance graph of the Earth. So by applying the same concept, if I find the area underneath this graph, I'll get the potential, not the gravitational potential energy, just the potential. So from this idea and the definition of gravitational potential, we can say that the area that we are looking to find is this orange area right here. And from the definition, you can see that it's the work done per unit mass to bring it from infinity. To bring it from infinity till this point. And I just chose to bring it till point 2r. Okay, so what do you do to find the area under a curve? You integrate. Now this is not required in the A-level syllabus, but it's still a fun exercise nonetheless. After integrating, you get this right here. Phi equals negative gm by r. And since it's gravitational potential energy per unit mass, I guess I got repetitive right there, you don't really consider the mass of the object. It's always taken as 1 kilogram because it's per kilogram. Anyway, so if you plot the graph, this is how it would look. So if this is the potential at the surface of the Earth, so if you increase the distance if you move twice the radius of the Earth, then the potential would be halved. And it just decreases in that way. And at infinity, the potential is 0. Now, energy at infinity is 0 because if you look at the formula, as R increases, as you increase R, this value decreases, becomes less negative. As R increases till 0, this value minus Gm by R, as R increases till infinity, this value turns out closer to 0. It approaches 0. So we can say that potential at infinity is 0. Now, I guess I've mentioned all of these points have the same energy or same potential. It's because you can see from the formula itself, it's only dependent on the distance from the center, not on how much you move sideways. From infinity till the center or till that point, what is the distance that you have traveled? Okay, now from the diagram itself, you get, from this diagram as well as this diagram, you get another reason why the potential energy is going to be negative. Well, the graph that we used for the area was in the negative axis. So in math, the area under the x-axis is usually taken as negative. So it's logical for the gravitational potential to be negative. But there is another idea though. But we'll get there later on. Anyway, we have plotted for the Earth alone. This is literally the potential distance graph for the Earth. I have not mentioned it, but it could be applied to any spherical object. It's a similar idea. Okay, so we've considered for the Earth, but what about having two masses? Now we are going to consider the potential between the Earth and the Moon. R is the distance between the center of the Earth to a point P, and D is the distance between Earth and the Moon. And D minus R right here is the distance between the Moon and this point P right here. Okay, so before we add the complication to it, we need to set up some ideas to deal with first. So imagine this object, it has two forces acting on it. Now, if I tell you to find the total force acting on that object, you could simply add the forces, but you include the sign. If F1 is in the positive direction, if you consider left as positive, then anything that moves towards the right is negative. So if you add both, you can write it in this way. Once again, it's a trivial idea, but it's important to keep it at the back of your head. Potential, however, this force did care about the direction. Potential, however, does not care in which direction you're pulling it to. By its very definition, it's the work done to bring an object from infinity to a point. Now, you could consider infinity from any direction, but if you're still bringing it to the same point, you need to do the same amount of work. So the work done in order to bring bring a kilogram or a unit mass from infinity to this point P is negative Gme by R. Gme is the mass of the Earth, plus negative Gm by D minus R, which is due to the Moon. M sub m is the gravitational potential due to the Moon. So if you add these two up, you're going to get this graph. Now I guess you could explain this to yourself, this entire graph to yourself, just by looking at the formula. Now, if you want to find the potential energy, this graph is graph of potential, but if you want to find the potential energy, you just multiply it by the mass of the object whose potential you'd want to measure. So if you have a 10 kilogram object, you know that the potential at this point is, let's say, 50. It's negative 50, sorry. Negative 50, just multiply it by the mass, 10, and you get negative 500 joules. Now for the big question, why is gravitational potential energy negative? Why should it be negative? Why do you always consider it to be negative? Now first, we've clearly established that the potential energy at infinity is zero. Just by looking at the formula itself, as r increases till infinity, the potential increases to zero. So, thinking about it simply, if you move an object up, you are doing work on it. You increase its potential energy, as we have explained a couple of minutes ago. Now, the higher you go up, the higher its potential energy. Now, if you can literally increase the potential energy to zero, the higher you go, you give it more energy, and you're increasing its potential energy, and you increase it to zero, and that happens at infinity. So if you're increasing it to zero, that means potential energy everywhere, less than infinity. You can never really reach infinity. Less than infinity should be negative. There is no other way. Now, another way to think about this is an object approaching the Earth from infinity. So as it falls into the Earth's field, it gains kinetic energy, right? So, but you're not doing any work on it. But all what we know is that it has potential energy, and that potential energy is zero at infinity. I've repeated this several times. I guess it should be important in some way. Anyway, it's zero at infinity, and if no one is giving it energy, it must be using up its potential energy. So that means anywhere less than infinity, you have negative potential. Anywhere inside the field, you have negative potential just to keep with the conservation of energy. Now, it feels weird, right? That you had zero at infinity and you are still taking away energy. You're still taking away energy from potential. But the idea, I guess it's relatable in some ways, considering banks. So think of your bank balance. Well, in this case, it's mine. It's $0, and you spent $8,000 on something. I'm not sure what that is, but really $8,000. So you did spend $8,000, and where did that money come from? From your bank, really. So you had zero, but you still spent $8,000. That means you took a debt, and because of that, your balance right now is negative. So thinking of debt again, if you consider that it increased its kinetic energy as it went towards the Earth, so it spent its energy on kinetic energy. So it had zero at infinity, so it had a potential debt. I guess that sounds weird, but I guess you do understand what I mean. So with the gravitational field done and gravitational potential done, I guess it's safe to assume that electric potential would be much easier because you've learned what the gravitational potential is, what potential energy is, and what field strengths are already. Now, for electric potential, you have a few different conditions. First, there are two types of charges, positive and negative. So you have multiple different ways to consider. So just like gravitational fields, electric field strength, so I guess I did not mention it in previous video, electric field strength is denoted by E. It's force per coulomb of charge, per unit coulomb of charge. Now, the potential is the work done per unit coulomb of charge. Now, this unit coulomb is always as a test charge. So they decided to go on for a more specific version of it. Now, the final idea is this. If the force is attractive, if you have an attractive force, potential energy is negative, as you have seen in the gravitational field. Gravity is always attractive, so the potential is negative. But with electric potential, you find repulsion as well. It's not always attraction. So that means you can have positive forces as well. And at the same time, you can have positive potential energy. If you have a repulsive force, you will have a positive potential energy. So let's consider this negative charge right here. And the force is attractive, so you have to do work to move this 1 coulomb charge from the surface of this negative charge. To move it away, you really need to give it energy. So from the surface to infinity, you would need to do a lot of work on it. And at infinity, it's always established at infinity, work is 0. So that means it's negative. Now you can think of it as really moving from infinity. If this point is infinity, moving from infinity to the point, it's losing energy, but it's speeding up, much like going down a hill. So, like the one above, if I bring a test charge from infinity to this positive charge right here, and energy at infinity is 0. I've repeated it so many times right now. Anyway, but because this time the force is repulsive, I'll have to push it against a force. Really, I'll have to do work. I'll have to push the charge to bring it closer to the positive charge, because these want to stay separated. So the potential is going to be positive for positive charges. So from infinity till here, you will have to do work. So the potential energy of this object, of the charge, is going to increase. It's like going uphill, like you need to push it, but you're increasing its potential energy. Now, just a final note, electric potential is the work done. I'm just saying the definition. Electric potential is just the work done to bring a 1 coulomb, a positive 1 coulomb of charge from infinity to the point. This point could be any point inside the field. So I guess that's all for today. And if you really stuck for that long, thank you for really watching this video. So in the next video, we'll go over graphs of electric fields and